Hello, everyone. My name is Brian Jackson. I'm currently a PhD student at Carnegie Mellon University. I actually just transferred here from Stanford with my advisor, Dr. Manchester, who's teaching this class. And so the purpose of this video and the accompanying cheat sheet is to help you as roboticists or in general scientific programmers to come up to speed in Julia and be able to get started on the assignments for this class, and in general just be able to start using Julia to solve real problems. So this intro assumes a solid understanding of scientific computing and a high level of proficiency in a language such as Matlab or Python. So I guess the first question to ask is why the heck are we using Julia? So why Julia in the first place? So I guess I want to try to answer that question first with a question to you. So when you run across a new algorithm in a paper or perhaps in a class or a textbook, what language do you turn to first when you want to implement it, when you want to prototype something? Most people, this is Python or Matlab. Why? And there's a long list of reasons. They're really easy to use. There's a lot of great packages, good IDEs, etc. But inevitably, in scientific computing and especially in robotics, we care about performance. So what do we do when performance becomes critical? For example, we want to put it on on an actual piece of hardware, on an actual robot, and have it run in real time. So there's really, if you're coming from Python and Matlab, kind of two options available to you to improve performance. One is to kind of ink all the performance you can out of using techniques like loop vectorization, or kind of depending heavily on packages like SciPy, NumPy, or TensorFlow. But really that can only get you so far before you're really at the mercy of what they've already implemented. And so the other option is to then go ahead and implement your code in a performant language such as C or C++, or Fortran if you're a little old school and a little crazy. So Julia attempts to solve this kind of so-called two-language problem by offering a very convenient, powerful syntax that, in my opinion, is kind of takes the best of both Matlab and Python while still offering very exceptional performance. So therefore, we can prototype quick and get things working, and then when we care about performance, it's mostly already there, but we can then just kind of change some things and get performance very similar to C and C++. So this is, for example, this is kind of like a set of benchmarks all compared to C. And here you have Julia and some other like recent state-of-the-art languages. And then over here you have Matlab and Python. So obviously we all know that these are slow and you want to avoid things like loops. But really, when push comes to shove, Julia is fast and can be as fast or faster than C, depending on what you're doing. So on a high level, how does it compare as a language? Obviously, C++ is statically compiled. Matlab and Python are dynamically compiled. Julia is somewhere in the middle. It uses a paradigm called JIT, or just-in-time compilation, where essentially the first time you run it, it'll compile the code and stash it somewhere, and then every time after that you call that method, it'll be fast. So another big difference between these languages is the age of the program itself, or the language itself, sorry. So the other three languages have been around for 30 plus years. They have massive user bases and lots of contributions on places like Stack Overflow. Julia is barely 9 years old. So it came out of MIT about 9 years ago. And that's being generous because version 1.0, which is the first officially stable version, was released in 2018, so during my PhD. So that being said, it really does have like a great community. If you want to find answers to your questions, you can post on the Julia discourse and you'll get answers. They're a very responsive and very helpful and friendly community. And then as far as object-oriented, obviously C++ and Python both are. Matlab, meh, it kind of is, kind of isn't. And then you have Julia, which is not object-oriented, but instead uses a paradigm called multiple dispatch. So we'll briefly talk about this at the end of this video. But really, the key takeaway here is that it's not really limiting. You can use it very similar to how you would object-oriented program. It's just kind of a different way of approaching it and offer some different types of behavior. And this last one is just kind of silly. For whatever reason, the authors of Julia decided to go with one-based indexing rather than zero-based. I know, I roll. But really, I've just gotten used to it, and it's not a deal breaker for me. And last but not least, for installing Julia, it's very easy. You just go to the Julia website up here, and you go to download, pick your the distro of your choice. You're going to download it, and then you're going to extract it into a place that you'll keep it, because this will actually contain the binaries. And then all you have to do is add it to your system path. So I'll just briefly, so I've already added to my system path, and once it's on your path, then you'll go ahead and type in Julia, and this will pull up the so-called REPL, or the interactive terminal. So from here, there's a couple options. Over here, if you hit the right square bracket, this will pull you into the package manager, where you can manage your virtual environments and add or remove packages. And then if you use the question mark and then type a command like plus, it'll give you the doc string for that command. So pretty basic. And I just a quick note is that do not install Julia from the command line using like sudo apt-get. It's much easier to just download it from the website and link it to your path, and that way you know that you're getting the latest version of Julia. So another reason why Julia is great and why we're using it for this class is that there really are a lot of great packages in Julia for scientific computing, and in particular around optimization and linear algebra. And they all just like play very nicely with each other. For example, there's the jump.jl optimization modeling language that kind of allows you to set up optimization problems very easily. And then you can solve it with a bunch of different solvers. So just quick example, let's say I wanted to add IP-opt. All I have to do is come in here to the package manager, type in add IP-opt. It'll download it. It'll download the binaries, install them, and compile them right there on my machine. And really, this is so nice when you're using kind of packages from lots of other programming languages, such as C or C++, and you don't have to worry about getting the right compilers or all the dependencies. All of that is taken care of for you with Julia. Another package that is really great in Julia is the differential equations.jl package. If you're coming from Matlab and are familiar with ODE 45, it's essentially that on steroids. It's the state-of-the-art package for solving differential equations, anywhere from like stochastic to neural net ODEs. It can handle all of that very fast again. And then another great package is the forward diff package, which we'll probably be using in this class. Just due to the way that Julia is set up with multiple dispatch, it makes implementing forward mode, automatic differentiation, and reverse mode for that matter, very easy, very fast, and very efficient. And so this allows you to easily get things like gradients, Hessians, and Jacobians for your functions and feed those directly into your optimization algorithms. And it'll still be fast and more accurate than doing finite differencing. All right, so now we are ready to start digging into some of the basics. So this section will now be kind of paralleling the cheat sheet that accompanies this video, which you should have already received and looked at. And yeah, so we're going to start talking about some of the basic numeric types in Julia. So if we go over here to the Julia documentation, you can see here that they have all of the integers that you'd really need, all the way from 8 up to 128 signed and unsigned integers, as well as Boolean values. You also have half, single, and double floating point numbers. So now we're just going to kind of look at some of these in a little bit more detail. So I'm going to open up a terminal. So I'm going to go ahead and move into a temporary folder called test, boot up Julia inside of that folder, and use the right square bracket again to move in the package manager. And use the activate command, and this will activate a virtual environment in my current folder. I can use the backspace to go back into the REPL. So now I'm going to be using the type of command here a lot. So this will essentially return the type of a particular value. So if I do type of 1, it'll show me that's a 64-bit integer. And if I do a 1 point, it'll be a float 64. So just a quick note here is that by default, Julia will be using double precision ints and floats. If I want lower precision floating point numbers, for example, I can do 1F0 as the suffix, and that'll be a float 32. If I want lower precision integers, I can do specify them with hexadecimal, and this will actually be an unsigned. Actually make it a valid hexadecimal. And then if I add in more bits here, then it'll go from a 16 to a 32 to a 64-bit. I can also specify things in binary if I want. And yeah, so really nothing surprising there. It has all the functionality that you'd see in other languages. For complex numbers, you can use the im suffix for imaginary numbers, and those can be floats or ints. And then they also have a fun little thing they have rational numbers. So I can use the double divide symbol, and this will create a rational number. So if I do 1/2 plus 1 plus 3/4, it'll do rational arithmetic for me. Don't really use that all that often, but it's kind of fun. And then they also have irrational numbers, so like or constants like pi that will match. Basically, it'll be a 32-bit version of pi or a 64-bit, depending on what you're operating with. Another thing that I really like about Julia is that they have Unicode support. So I can use the pi command, use tab completion, and get the pi symbol. I can also do this for Greek letters like theta and assign values to them in my code, which can really help with code readability and translating algorithms in papers to actual code implementations. And then as far as basic operations, there's really nothing surprising here. Everything's pretty much the same with maybe the exception of, let's say if I have a is equal to 2, I can do 2 times a. I can also shortcut this using some syntactic sugar and just do 2a, and that'll shortcut the multiplication there. If you're coming from Python, exponentiation is the caret, not the double star. And then for division, if I want to do floating point division, it's always the divide symbol, even if the values themselves are integers. If you want integer division, you can use the div Unicode, which will give you integer division if you want that. Okay, so that's pretty much it as far as the basic numeric types. And then Julia also has very well documented and kind of lots of functionality built around strings. We don't use strings that much in scientific computing, but I'll cover some of the basics. So you can create a string using double quotes or a character using single quotes. I can index into a string to get a character, or I can get a substring using a range. Nothing too exciting there. And then as far as, I mean, mostly when we're working with strings in scientific computing, it's actually working with file paths. So there's, if you ever seen anything in Julia with an @ symbol in front, this is called a macro, pretty similar to macros in C and C++. So this one will give me my current directory. There's also one for a file. And then some other handy things for working with file paths. There's the join path command that's in base Julia. You can put together a file path just like that. It's the only kind of weird thing about strings in Julia is concatenation, which actually uses multiplication or the star rather than addition. So you may think this is weird, but it actually has a very good logical reason behind it. So if you think about the mathematical properties of addition and multiplication, so addition is kind of by definition commutative, meaning I can swap the input arguments and I should get the same output. String concatenation is not commutative. So technically we can't use addition and should be multiplication because multiplication doesn't have to be commutative, like for example with rotations. Another thing to be aware of in Julia are symbols. So these are basically hash strings. So you can create those using a colon and then a string of characters. So being hashed strings that you can't index into them or get characters out of them, they're only good for testing whether or not one is equal to the other, for testing equality. So in this sense, they're very similar to like enum types that you would use in C or C++, and you'll see those pop up pretty frequently in Julia code. Now for printing, really nothing too surprising here. We can use the print line command to do have a new character at the end of the string, or just a regular print command, which will leave that off. If I want to interpolate values, let's say I have the value of a is equal to 2. I can print a is equal to, and then pass in that variable as the second argument, and it'll do it like that. You can also interpolate values, which is using the interpolant symbol, which is the $sign in Julia, and then it'll interpolate the value. I can also interpolate any expression using by surrounding it with a parenthesis. So for example, I can do a plus 2, which will be 4. Now, if you're really used to printf and you want to use that, you can pull that in using the printf. Spell that right, printf, and that'll allow me to use the printf macro. So here, if I do a is equal to 0.2f, and then we'll do it on pi, and there you go. That works as expected. So nothing too surprising there. I guess one little fun thing to wrap this up, if you want to get a little fancy, there's a print styled command, which allows you to do something kind of cool. I can do bold is equal to true, and I can even set the color to red, and it allows me to print styled strings to the terminal, which can be kind of fun if you want to spruce up your output. All right, so now we're on to arrays, which are really going to be the bread and butter of what we're going to be working with in scientific computing and in this class. So Julia really has like all of the functionality that you'd want in arrays. Quick note, like Python, they differentiate between one, two, and multi-dimensional arrays. So for constructing those, they have some fairly simple syntax. So if you want a column vector or a 1D vector, here I just use commas. If I want a row vector, which is going to be a two-dimensional array, I'm going to use spaces. So note here, there's a 2 here, meaning it's a two-dimensional array. If I want a matrix, I'm going to do both of those together. Now, if I want to reshape, I can do that. Point reshape on A, and I could do a 4x1. Or if I wanted to flatten it, you can use the vec command, and that'll flatten it into a one-dimensional array, whereas the reshape was into a two-dimensional array. Also, just a quick note on reshape, if I want to infer the size of one of the dimensions, I can use the colon operator, and it'll do the automatic inference for me. They also have a bunch of really nice initializers, the unsurprising, zeros, ones. Now, if I want to change the type of these, I can add in a type as the beginning. So for example, if I wanted a bunch of 0 integers, I can add in the type as the first argument, or here I could do a uint 8, or I could do an int 8 if I wanted. And then they also have some other ones like fill, which will fill in a value of the appropriate size. This will fill in a matrix of tens of dimension 3x4. They also have rand, which you've already seen. So here, a rand vector or a rand matrix. If I want to do a Gaussian or normal Gaussian, I can do rand n. Another fun thing about, sorry, before I say that, they also have ranges, as you've already seen. So here I can do like 0 to 10. If I want to get all of those together, the best way to do it is using the collect command, which will work for any iterable collection and turn it into a vector. I can also do this as a step. So here I can step by 2. Sorry. Now, if I want a generic ability to create ranges or lin spaces, as you'll see them in Matlab or Python, I can specify the start and then the stop, and then I can do the step of 0.1, and then I'll do that, or I can specify a length for like 101. Oop. My syntax here. So those can be very handy. Now, if I wanted to, for example, sample from a particular range and create a sample of that size. So for example, if I wanted to sample all integers from 0 to 15, I could pass that as the first argument. And now I can pass in the size as the remaining arguments, and that'll work. So that can be handy when you're putting together some matrices. They also have, like Python, list comprehension. So if I want to do like 2 times I for I is equal to 1 to 10, I can do that. I can also do this with multi-dimensions. J is equal to 2 to 3, or whatever. I can also do, they also have a map command. So if I wanted to take the sign of everything in, a random value of, there we go. Also, they have this convenient do syntax in Julia, which essentially for any method that takes in an anonymous function as the first argument, I can move that to the outside. So here I could do map of A, and here the syntax is do A, where the little a is the elements of the collection that I passed in. So here I could do sign of A plus 2 times A, I don't know, it doesn't matter. And then I can do as many lines here as I wanted, and then it'll output the last line, and it'll apply that operation to every element. Another common thing that we might need to do, for example, would be creating like a vector of vectors. So here, I can do that very easily, and this will create a vector of vectors. All right, and now for basic operations on arrays. So here I'm just going to create a couple basic arrays. And they support things like push. So here I'm going to push to X, push 10 to x to the end. Also, I can append, which is similar to push, except it's expecting another iterable collection. So here I can append two vectors, which essentially just concatenation in this case. They also support things like maximum, so I can call it maximum of x. I can do argmax of x, and it'll give me the index of the maximum if I want both at the same time. I can do find max. I can also call things like reverse. Now in Julia, notice that here if I reverse x, the original x is not changed. Now if I wanted to do a mutating version, I'm going to call reverse bang or reverse exclamation point, and this will actually invert the matrix in place, or the matrix or the vector. So just this is just by convention in Julia, any method that ends with a bang is mutating, will mutate one of its arguments. Another, if we want to do like basic operations like arithmetic, of 3, 1, 3. If I wanted to add these two things together, I can do that. Add, subtract. Now, if I want to do multiplication, multiplication between two arrays defaults to matrix multiplication, so it will be ill-defined for these. If I want to do element-wise, if you're coming from Matlab, this will be very familiar. I can do dot times, and it'll do basically broadcast that operation element-wise. This also works across the board. So if I can do x dot squared, for example, I can also do any unary function. I can put a dot in front of it, and it'll apply it element-wise. Again, this dot is really just a broadcast operation that says do this for every element. Now for assignment, I've kind of hinted this at a little bit, but Julia passes things by passes immutable types by value and mutable types by reference. Essentially, it passes by reference, but since immutable types can't be changed, it passes them by value. By immutable types, I mean things like integers, floats, tuples, things that kind of by definition you cannot modify. Really doesn't make a difference if you pass them by value or by reference, but basically what this means is unlike C or C++, where you could modify an integer in a function, you cannot do that in Julia. And then, so as far as assignment, like Python, if I assign B to A and then modify the first element of B to be 10, this will modify A. So this is their alias together. It's really just looking at the same memory underneath. Now let's say I wanted to create a new array C, the right size. I wanted to copy to that. I could do copy to C from A, or I could say A is equal to copy of, or C is equal to copy of A. Now, obviously, if I change C, it won't change A. If I wanted the other alternative to this, if I have some matrix C and I want to copy all of the elements, I can use a dot equals, which you'll occasionally see in code. And this will be basically it's an alias to copy to. It's again, using that assignment equal or assignment operator element-wise between the two matrices. Now for testing equality, obviously these two things are going to be the same. This is going to be looking at element-wise over everything. If I want to look at all the elements, I can get the bit array there, and it'll look at all of those. Now, if I wanted to look to see if they're the same memory underneath, basically pointing to the same pointer, I can use the triple equals, and this obviously is false, whereas if I do this for B, this is going to be true. So that can be a useful shortcut or thing to know about for testing equality between arrays. Now, in terms of slicing and indexing, they support pretty much all the methods you'd want. So here, if I wanted the first column, I could use the colon and then 1, or I can use ranges here, and that'll work as expected. I can also use Booleans. And I guess one other thing about indexing in arrays is Julia allows both linear and Cartesian indexing. And I should have noted this earlier, but Julia, unlike Python, is column major rather than row major. So remember that when you're reshaping and when you're using linear indexing. So well, again, let's look at the value of A. Say we wanted this value 2 here. I could obviously do first row, second column, and that would grab 2. Or I could do the third linear index, because again, it's one base indexing, so 1, 2, 3. And again, column major. And then Lastly, let's say we are working with a large matrix, say let's say a sparse matrix. So let's load in some sparse arrays. This is just part of the standard Julia package. Let's create a large matrix B, P zeros, let's say 100 by 100. All right, so now let's say we wanted to take a view or like take a chunk out of that and modify it and have it still modify the original parent. So we can do that by creating a so-called view in Julia. That's basically like a subarray. So I'm gonna take a view of B and let's say, I don't know, like 4 to 10 and then 50 to 60. So that'll grab that chunk out. Now I can modify B bar. Let's say index 5 is equal to 10. Now, if I look back at the original B, you'll see that it inserted that value into the original B because this is just basically a view into the larger matrix. So views can oftentimes be much more efficient than slicing, which will do copying. So if you want to avoid that kind of excessive memory copying or whatever, a lot of times a view is the way to go. Okay, so now that we've covered arrays, we're going to move on and talk about linear algebra and some of the built-in stuff in Julia. So in order to use that, we're going to pull in the linear algebra package, which again ships with Julia, so we need to install it. So this automatically allows, opens up several new types that we can work with when it comes to arrays, particularly matrices. So if we want to create a diagonal matrix, we can do something like that. So pass it a vector, or let's say I have my, let's do like a slightly larger matrix here. If I want to get the diagonal of that, I can do diagonal of A, and then I'll create a diagonal matrix of that or of that data. Similarly, I can do this for like symmetric of A or lower triangular of A. So as you can see here, this is creating new types, basically new objects that use the underlying data of A and create the lower triangular portion or the symmetric version of it. So when you call things like invert or trying to solve a linear system using these types, it'll automatically giving information to the to the compiler or to the methods of like what methods to use. For example, if I have a lower triangular matrix and doing an inverse on that or solving a linear system, it's just like a backwards or forward substitution, which is much more efficient than trying to invert the whole matrix. So whenever basically end of this like summary here is use these types when you know what types of matrices you're working with, because they can provide extra information and can help with some storage underneath as well. Now, there's also some basic operations. So let's just create a couple of vectors here, 3 vectors. Now, if I want to do matrix multiplication, I have my matrix A, let's create a matrix B that's like a 5 by 4. If I multiply these two together, this will be matrix multiplication. So obviously if I do B times A, this will not work because they're not the right size. However, I could do B transpose times A, where the transpose is just the apostrophe there. I can also leave out the multiplication symbol here, and it'll do transposed multiplication, just a little bit of syntactic sugar there. And similarly, I can do the same thing for vectors. So I can do x transpose x, which would be the 2 norm squared, or x transpose y, which would be the inner product. I can also do the outer product. So times y transpose will obviously be the outer product. I can also do cross using the Unicode times, or similarly cross y. You can see those are the same things. So I can also get the eigenvalues, which is another common thing that we'll want to do. You'll see a little bit later, there's a better way to do this, but if you just want to get them, that's the easiest way to do it. Now, so, I mean, nothing too surprising there. Oh, I guess I should mention norm. So this will default to the 2 norm, but I can also pass in the P norm that I want. So I could do a 1 norm, I could do an infinity norm, or any other norm that I wanted. I could do a generic P norm, and all those will work. Now, typically we're going to be solving some type of linear system. So this is kind of ubiquitous throughout robotics and scientific computing in general. It could be a least squares problem or whatever, but we're always trying to solve something of the form AX is equal to B. So now we have A, so let's create a B vector here that's of the right dimension. Now to solve AX is equal to B, borrowing from Matlab, we can use the backslash operator, and that'll solve that system. Now, this is the underneath the hood. This will basically be looking at the underlying structure of A and B, whether or not you've specified, things like symmetric or triangular or whatever. It'll do the best to figure out the appropriate method to use, and then it'll use that. So this is a generic method that is oftentimes like the best first thing to do. And I should also note that this works with least squares and least norms problems. So let's say we have rand of 10 by 4, or sorry, a 5 by 3 matrix, and then I solve this system. This is going to be the least square solution. Likewise, if I do a 5 by 10 and do a/b there, it'll be the least norm solution. So those work, can be very handy and a very quick way of solving those systems. Now, oftentimes we know a little bit more than just, I want to solve this system, and we want to do a little bit more efficiently or have a little bit more control. And usually we want to create a matrix factorization. So say, for example, we have a symmetric positive definite matrix, A. So I'm just going to create that this way. And so first thing to do is I need to make sure it's symmetric. So I can call it is symmetric on A, and that should be true. I can also check to see if it's positive definite, which is also true. And I can also check the rank, which is the last thing that we need to do, which it wouldn't be positive definite if it wasn't full rank. But you can just call the rank and it'll give you that. So now that we know all of those, we can take the Cholesky factorization. So don't worry if you don't know what that is, but a lot of you have probably already seen this. So here I can call Cholesky on that, and it'll notice it's giving me a Cholesky object. So here it's a Cholesky factor with this particular factor, which I can pull out of Chol A. I can do upper or lower triangular factors. Now, if I want to solve this system, I just call Chol A and do the backslash on B. So this, you'll see that this is the exact same solution I get out of B. But you'll see that it takes a significantly less time. So if I do at time, which is a shortcut for getting the time required to evaluate a particular expression. So here I'm going to do Chol A divided by B, and then at time Chol A, just regular A divided by B. You'll see that it took significant or a good chunk less time to do the Chol A. And this will grow a lot with the size of the matrix. Again, because we've already performed the factorization, which is the most expensive part of solving the system, and now it's just doing simple forward-backward substitution for this system. So that's oftentimes what you want to do. So say, for example, you have some constant matrix that you want to solve a bunch of times for like several different input vectors, then you'll just compute the factorization once, cache it, and then use that, and then you just use the backslash on that. So this works for all types of matrix factorization. So I could do, like, for example, a QR of A, and doing QR of A backslash B will return the least squares solution if this is a tall matrix or et cetera. So this is the generic way of the better way of solving linear systems in Julia. Now, if I wanted to get the individual matrices out of this, again, I can do QR dot Q dot R. If I want more information on all of these, I can do help QR. You'll see that pops up a bunch of information on all of these for sparse matrices, whatever. I can change the block size, all the details there that I would want. Again, there's also SVD, there's eigen. I should just quick note on the eigen decomposition. If I want to take the eigen of that, I can do E dot values and E dot vectors. And so this is technically the better way of doing it because you store both of them together in the same place. So now that we've covered arrays, basic types, and linear algebra, we're ready to kind of dig a little bit more into Julia, and we're going to talk about functions. So we'll kind of give an example of writing some basic functions, and then talk about some optional keyword arguments, and then talk a little bit of multiple dispatch at the end. So let's just say we want to define a function, which you've already seen this a little bit. So we're just going to do my sum of x. I'm going to do something a little fancy here to be a little bit more efficient. I'm going to call my output here, I'm going to call the 0 function on the L type of x. So essentially what this is doing is this is looking at the whatever, so x is some collection, and it's going to be a collection of some element types. So this could be int 64s or float 64s, or this could be other vectors, whatever. So this will take a 0 or whatever that type is. And now I'm going to loop, so I can do a for a in x, or if you want to be fancy and use the Unicode, you can use that for whatever reason. Now I'm going to do out plus equals to a, end that, and then I'm going to return out. Note that in Julia, you don't have to specify return. If it's the last expression in a function, then it will return it. So here I could just put out, and that'll work. Now, I'm going to pass in a vector. So we're going to do rand of 1,000, and I'm going to time it the first time to here. And notice it's actually not that fast, but if I call it the second time, it's going to be blazing fast. You'll see the allocations went down, the memory went down, and the time went down a lot. This is because this first time I called it, I had to compile it, basically cache that compiled code, and then the second time, it's just calling that code that I put together. And so now for kicks and giggles, let's do some comparison to Python. So I can actually call Python directly from Julia, which can be nice for some of you that are more familiar with Python. So here I can do add PyCall, which I should have already added. So it should go pretty quick once it's done some checks. Now I'm going to start using that one. So this allows me to do several things. You can look at the documentation, but I'm going to import NumPy. Oops, sorry. Not what I'm doing here. Py import. There we go. And there we go. I've got NumPy. And now I'm going to define a method directly in Python inside of Julia. So I can do that using this py string. And I'm going to put together a py sum of x. Very similar to what I had before. For a in x out plus equals to a. There we go. So that'll define that method. Now I'm going to use a different package to kind of benchmark these results. I'm going to use the benchmark tools package, which basically run timing results a bunch of times. Let's just add b time, and let's call it on our Python method that we just defined. I'm going to interpolate the value in. Don't worry about too much about that. That's just kind of syntax recommended for b time. Basically, it takes it out of the global scope and puts it into the local scope of the function. So we'll have this run the first time, or you don't have to worry about just-in-time compilation. The b time will automatically take care of that and exclude the first time. So, you know, pretty slow, nothing too surprising there with kind of built-in Python. So let's do the NumPy sum. And we can do that. We'll see how that timing result comes up. And obviously we're expecting this to be a lot faster than, you know, our naive implementation. Now let's try out the sum that we wrote in Julia and see how that does against NumPy and Python. So this might be a little surprising to you, but it's actually way faster than both NumPy and obviously the naive version in Python. So it's about 6 or 7 times faster than NumPy, just this simple version that we wrote, function that we wrote up there. And for kicks and giggles, let's see how it compares against the built-in version in Julia. Notice this is going to be really fast. This is going to be calling like very low-level optimized sums on like directly on the hardware kind of stuff when using pack and blast. So obviously it's going to be very fast. But in summary, the key idea that I want to drive home here is that loops in Julia are fast. As you can see here, we got similar performance in NumPy just by putting together a loop. So you don't usually need to like worry about vectorization or anything like that. If it's naturally expressed as a loop, just go ahead and write it as a loop. It makes it easier to read, to debug, all of the above. And so yeah, don't worry about vectorization essentially in Julia. You can keep things as loops and it'll work just fine. So now talking about positional and keyword arguments, if you're putting together your own function, or you'll see other people's functions. So I'm just going to call it like my fun of a and b, and then I have an optional positional argument c with a value of 10. Now if I want a keyword argument, I put a semicolon and then I put my key value pairs. So I'm going to default to that. And here I'm just going to print out the value of c and the value of verbose. All right, so now if I call my fun with only 2 arguments, then it'll print out those default values. Now if I put in a third argument, it'll change the value of c. If I put in verbose is equal to false, then that will change. Now notice if I try to put in false without the keyword, then it won't work, unlike Python. But I could do verbose is equal to false and leave out this positional argument, and those will all work. And now lastly, there's the thing called var args. So here I could do a function var of x dot dot dot. Essentially, this will allow me to pass in positional arguments as a vector. So now I'm just going to print out the length of x. So if I pass in 1, 2, 3, it'll print out 3. I can pass in 2, 2, etc. So this is called splatting in Julia, kind of similar to the splatting that you'll find in Python. And this will work also when I'm calling functions. So for example, if I have a tuple integers here, I could call bar of t and splat that into the positional arguments, and it would work as expected. Now note if I don't splat, I've only passed in one argument, so the length of the arguments would be 1. Now, so that pretty much covers the basics of functions in Julia. We're going to try to cover a little bit and give you a little bit of intuition as to what multiple dispatch is and how to use it. So the key idea behind multiple dispatch is that if you're coming from C or Python and more familiar with some of the advanced features around around objects and object-oriented programming, you'll know about operator overloading. This basically allows you to define things like subtraction, addition, multiplication for your specific like custom user-defined objects. And essentially, multiple dispatch allows you to do that for everything and automatically pick the method of a particular function for the most specific matching types. So that might be a little abstract right now, but let's look at it in a little bit more detail. So let's say I have a function foo. So here I'm going to use the inline version of function definition, which allows me to be a little bit more succinct. So I'm going to pass in 2 arguments, and here I'm just going to print out a generic method. So now if I do foo of 1 and 2, it'll print that out. Notice I didn't specify any sort of like limitations on the types that I can pass in, so I can pass in anything I want, and it'll work. Now let's say I wanted to do something special for integers. So I could do an integer, y integer, and let's print both ends. Now if I call foo of 1 and 2, which are both integers, those will work. And I could do an unsigned integer too, and this will, since it's still an integer, it'll work. Now note if I try to type it, like pass in a float, it'll fall back to the generic method at runtime. So I can get as crazy as I want. So this is really the key idea. So let's say I wanted x to be a vector and y to be a string. I could print out vex string. And let's pass in 3 and a, and there we go, we get a vex string. Now notice if I change this to a matrix, this is no longer a vector, so it'll fall back to the generic method. So that's really the key idea behind multiple dispatch, and you can get object-oriented like behavior and things like inheritance by setting up your own and defining your own custom types, which we won't cover here, but you can look it up. It's not too bad. And then defining methods on those custom types. So this idea in general can be very powerful, and it can actually translate to making kind of mathematically based code easier to implement, easier to understand, and easier to work with. So hopefully this you'll find this kind of intro helpful as you get started programming in Julia. If you have any questions, feel free to reach out to me during office hours or via email, and I'm happy to help. For example, if you're interested in learning more about multiple dispatch or how all this works kind of behind the scenes on the type system, again, I'll be happy to talk about that offline. So I'll catch you on the other side. Bye.